Okay, so in the video today, we're going to look at spectroscopy, organic spectroscopy specifically. How do organic chemists know the structure of their compounds? Prior to about 1950, structural assignment was a very difficult thing to do. What you could do is you could determine the formula through combustion analysis, analyze the amount of carbon dioxide and water that's produced when you burn something, and that would tell you the percentage of carbon and hydrogen in your molecule. You could determine the molecular weight through various processes like freezing point depression and titration for carboxylic acids and amines and various other methods. You could determine the presence or absence of functional groups through chemical test, and you could compare two compounds and determine whether or not they were identical. Okay, modern day structure assignment is a much easier process thanks to advances in spectroscopy. Now, I like to say that this is the undergraduate level spectroscopy class. This is only one chapter in a book that has like 27 chapters. So I have to limit what I talk about. So this is only an overview. If you really want an in-depth, proper treatment of spectroscopy, you're going to need to take our graduate level class in spectroscopy. Okay. All right, so let's look at some of the basics of spectroscopy. This equation here is known as the Einstein equation. E equals hc over lambda, okay, or E equals h nu, okay, and this is the wavelength of electromagnetic radiation, and this is the frequency. The beauty of using frequency is the fact that wavelength and energy are directly proportional. That frequency and energy are directly proportional to each other. So we can make a direct correlation, whereas there's an inverse correlation for wavelength. Okay, so what happens when molecules absorb electromagnetic radiation is that they go from what we call a ground state configuration, where the whatever our situation is, whether it's a vibration or a electronic position or a spinning direction for one of the methods we're going to be talking about, is in the lowest energy situation. And if you hit it with exactly the right amount of energy that corresponds to the difference between this ground state and the next available excited state, okay, you can make this go from having the ground state configuration to an excited state configuration. And the amount of energy required to do that has to match the wavelength of the electromagnetic radiation. Okay? And that's a simple process that's going to be governing most of the things that we talk about in this section. Okay, so let's look at the electromagnetic spectrum briefly. Okay, so on the left side, we have the most intense short wavelength irradiation. Gamma rays are the most intense, X-rays followed by ultraviolet visible, which are really the same thing, it's just that you can see part of it, okay, followed by infrared, microwave, and radio frequency radiation. Okay? All right, so what's going to happen here is that we're going to look at what specific types of radiation do. For instance, radio frequency affects nuclear spin in a magnetic field. Infrared affects vibrations, and ultraviolet visible affects the electron configuration. Okay, and we're going to talk mostly, most of this discussion of spectroscopy is going to be centered in this latter one here. We're talking about the nuclear spins in magnetic fields, okay? And the most important method of spectroscopy, nuclear magnetic resonance, is based on radio frequency irradiation. That's the one we're going to talk about first. Okay, so let's begin talking about nuclear magnetic spectroscopy. Molecules that have odd mass or atomic number, their nucleus creates a magnetic moment when it spins, okay? So when we apply a magnetic field, our nucleus can line up, align with the field or opposed to the field. And this is a slightly higher energy, the opposed, over the aligned, okay? So this is where we have our excitation going from the aligned to the opposed spin configuration. All right, so if we look at configuration A, it's in equilibrium with configuration B. Remember this important equation here, delta G equals minus RTL in K. So A is going to be the lower energy or the ground state, and B is going to be our excited state. Okay, the energy difference here is actually quite puny. Okay, so if we have this many atoms, 1 million atoms at 25 degrees, and we're going to say our magnets of the size of 300 megahertz. I know you're probably wondering, magnets aren't measured in megahertz, that's the frequency unit, but we'll talk about that in a second here. But the A to B ratio isn't terribly different here. It's 5 million if we have 10, actually, no, this is 10 to the 7 hydrogen atoms, sorry. Okay, it's 5 million and 250 versus 4,999,750. Only 500. We're only looking at the excess ground state population. If we subtract these numbers, it comes out to be 500. So we're looking at a very small percentage of the molecule. So NMR is the hardest, produces the weakest signals of all the spectral methods. So there's a lot more sophistication in the instrumentation for an NMR spectrometer. Okay, let's look at odd mass or odd atomic number. What are some common elements that have this property? Protons. Deuterium has an even mass but an odd atomic number of 1. Carbon 13. Fluorine 19. Phosphorus 31. Okay, and these are the two elements that we're going to focus on as we discuss NMR. So we're going to look at proton NMR and carbon NMR. Proton NMR is by far the more important of the two methods. Okay. All right, so NMR goes a lot deeper than what I'm talking about here, but I want to get to how it affects, or how organic compounds affect the NMR spectrum. That's going to be the focus of this section here, not the physics involved with magnetic absorption. Okay? All right. So here we have a graph that's showing us what happens to the energy difference between the excited state and the ground state as we increase the magnetic field strength, okay? Okay, so they get farther and farther apart. The energy difference between the excited state and the ground state gets farther apart. And that's a very important consideration because look here, I said at a certain field strength, there's only 500 excess molecules in the ground state. Well, if you increase this energy, the excess ground state population increases quite dramatically. Okay, one other comment. Why are we measuring magnetic field strength in this unit of frequency? Okay, so magnetic spectrometers their power is gauged by what frequency is required to excite a proton. Okay. All right, so the 300 megahertz magnet has a magnetic field strong enough that it requires 300 megahertz to make your average hydrogen go from the ground state to the excited state. Okay, so that's why we're using frequency units to describe what should be in Gauss or Tesla or something like that. All right. Okay, so let's look at what makes NMR so useful. All right, so we're going to be specifically talking about proton NMR. Individual hydrogen atoms have slightly different absorption frequencies. So let's look at two extremes. Here's chloroform over here. And what you see here is that this carbon has a lot of electron withdrawing groups on it that are pulling the electron density away from carbon. And therefore, the bonding electrons in the CH bond are spending more time at carbon than at hydrogen. This carbon here is fairly electronegative as far as carbons go because the electrons at this carbon are being pulled away by the chlorine. So there's a partial positive at this carbon. And this hydrogen is feeling that partial positive. Okay, let's look at another extreme. This is a compound called tetramethylsilane, or TMS. It's a very important compound. It's the reference compound in NMR spectroscopy. Okay, what we have here is silicon is below carbon in the periodic table and thus less electronegative. So carbon is pulling electrons away from silicon. These hydrogens are also less electronegative. Notice that I've emphasized one hydrogen, but all 12 of the hydrogens in tetramethylsilane are actually equal to each other by symmetry. Okay, so this hydrogen is attached to a partially negative carbon, and these electron pairs here are going to be spending more time around hydrogen. So the effect here is that chloroform is attached to a carbon atom with low electron density. The hydrogen nucleus is exposed because this electron pair isn't really shielding it anymore. So we say it's deshielded from the external magnetic field, and it's going to absorb at a lower energy or frequency. Tetramethylsilane is just the opposite. It has a high electron density. The CH bonding electrons are closer to hydrogen than in chloroform, and we say that this hydrogen nucleus here is shielded from the external magnetic field, and it's going to absorb at a higher energy or frequency. It's going to take more energy to penetrate the electron field set up by the bonding electrons. Okay. All right, so this slight difference of different hydrogen atoms is a term that we're going to call the chemical shift. And you either put the number delta in front of the number that you're talking about, or you refer to it as parts per million. Okay, and chemical shift is defined as the absorption frequency of the hydrogen of interest minus the absorption frequency of tetramethylsilane divided by the spectrometer power in megahertz. Okay, so we have hertz divided, sorry, let me put it at a better place. Hertz divided by megahertz. So this is where the term parts per million comes from. Okay, hertz divided by megahertz, or parts per million. Okay, so what are some things that affect proton chemical shift? It's electronegativity, the hybridization of the attached carbon, and the local magnetic field. And we're going to find that B is really due to C. All right. Here's a typical NMR spectrum. For a typical proton of an organic system, we're going to see the spectrum go from 0 to 10 parts per million. There's only one type of proton that we're going to talk about in the carboxylic acid chapter that comes outside of this range. So this is going to cover almost every type of proton that we see. So on the x-axis we have parts per million, and on the y-axis we have just a signal intensity or absorbance. Okay. As we go to the right, we're looking at increased shielding, increased frequency, or a higher field. As we go to the left, we're going to look at decreased shielding, decreased frequency, or lower field. These terms are often misused and a little bit confusing. Okay, so one way you can never go wrong is just to use decreasing chemical shift or increasing chemical shift. Okay, chloroform at 7.24 is higher than TMS, which is at 0. Okay, so so this is the NMR spectrum up here of a mixture of chloroform and tetramethylsilane, or TMS. Okay, one comes at 0, and chloroform, since it's in the vicinity of lots of electronegative groups, has a much higher chemical shift. Okay, so let's look at the primary effect on chemical shift, and that's electronegativity. All right, so let's look at some representative protons. Chloromethane is at 3.2, very similar to methanol. Hydrogens here. We'll talk about the alcohol hydrogen a little later, but these CH3 groups come at 3.4. Okay, nitrogen is less electronegative than oxygen, and the chemical shift is 2.6. Less electronegative than nitrogen is carbon, so if we replace this nitrogen with a carbon, we see the chemical shift dropped quite a bit to 0.7 parts per million. And hydrogen is even less electronegative than carbon, so if we replace this carbon with a hydrogen, we see the value go down even further to 0.1. Okay, the electronegativity effect is, for the most part, additive, but not completely additive. Here we have dichloromethane, it's at 5.3. Here, chloroform, it's at 7.3. What you'll notice here is that you don't get quite as much electron withdrawing power, right? So we go from a hydrogen to a chlorine, it goes up to 3.2, but the next one only takes us to 5.3. Okay, so it's not perfectly additive, but you can say the more of them you have, the higher your chemical shift is going to be. Carbon tetrachloride, you might say, is going to continue this trend, but no, it's not, because there are no hydrogens in carbon tetrachloride, so we don't have a signal. Okay, pi bond electrons generate their own little magnetic fields that interact with the external field in different ways. Okay, so for an aromatic ring, we're going to see the protons come between 6.5 and 8 for a hydrogen directly attached to a benzene ring. For an alkene, it's a little bit less, at 4.5 to 6.5. For an aldehyde, it's 9 to 10, and this is just a straightforward electronegativity effect. Okay, so this hydrogen in both cases is attached to sp2 carbon, but the one where the sp2 carbon pi bond is to another oxygen has a much higher chemical shift. Okay, we see hydrogens at sp carbon come in a totally different range here. Okay, so these come 2 to 3 parts per million hydrogens, the hydrogen of a terminal alkyne. All right, and finally, this hydrogen is attached to sp3 carbon technically, but there's an sp2 carbon adjacent to it, and what we see here is that the chemical shift is affected a little bit, not quite like it is here, but we see it's a little bit higher than it is in a comparable system here where the carbon is attached to an sp3 carbon. All right, now I just got to caution you about these chemical shift ranges. You got to keep an open mind for things coming outside of these ranges. There are things you can do to an alkene to make its chemical shift less than 4.5, and there are things you can do that'll make it come higher than 6.5. Okay, so these are just a general guideline. Keep an open mind for things coming slightly outside of these ranges. Okay, one last thing here. It's a little hard to look at the pi bond contour maps as to what they do to magnetic fields, but these two hydrogens here are in seemingly similar environments. So what makes them different is the interaction when you have an aromatic system, the aromatic protons, sorry, the electrons in the aromatic system precess in a way that creates their own little micromagnetic field. This is often referred to as ring current. And this pi bonding electrons create a situation where things adjacent or just outside the ring have a line with the magnetic field and they have a high chemical shift, and things that hang above the benzene ring, there are structures that you can generate that do have this property, have artificially low chemical shifts because they're opposing the magnetic field. So it's these micromagnetic fields set up by the pi electrons that are responsible for what we call this hybridization effect on chemical shift. Okay, chemical shift's not the only important aspect of NMR. There are 3 equally important aspects. Okay, so chemical shift tells us the hybridization of carbon for specific hydrogens and whether neighboring electronegative elements might be present. Another factor is signal number and integration, and this is a property we saw with intensity. Okay, this tells us a little bit about the symmetry of the molecule and the number of specific hydrogen types and their relative abundance. Signal intensity is proportional to the number of hydrogen atoms that are giving rise to that signal. Okay, all right, so let's look at the previous one here. Yeah, we'll just look at these two. All right, there are 3 hydrogens giving this signal here. There are 2 hydrogens giving this signal here. If you had a 1-to-1 mole-to-mole ratio of chloromethane and dichloromethane, you would find that this signal was 1.5 times as big as this signal because there are 3 protons contributing here, where there's only 2 protons contributing there. We're more interested, however, in the ratios within the molecule, not between 2 separate molecules, but you can use that to determine how much of something is present as well. Okay, the other thing that NMR, other information that we're going to get out of a proton NMR spectrum is signal splitting. And this is the last topic we're going to cover in the proton NMR section. Adjacent hydrogens will split the signal of a given hydrogen due to their own little magnetic moments. And you can tell how many hydrogens are on the adjacent carbons relative to the hydrogen that you're looking at. And we'll look at this this is perhaps the most important thing that allows us to determine one specific structure from an NMR spectrum. All right, so let's look at this integration issue. This is the molecule called acetaldehyde. We'll look at aldehyde nomenclature systems when you get to the aldehyde chapter. Okay, so here's the normal spectrum in black right here. Okay, we have a signal here at 9.8, that's for this aldehyde hydrogen, and we have a signal at 2.1, that's for this methyl group right here. Okay, so you can adjust the mode of the spectrometer to just measure the area underneath each peak. Okay, so we'll call this X. And if we integrate here, okay, sorry, that's not a really good straight line there, is it? This should be about 3x because there's 3 of these protons and only 1 of this one. So this one, when we do the integrate mode, should be 3 times as high as this one. We can actually get our spectrometer to digitize it, and we would find and the numbers underneath represent the integration values, okay? All right, so there are a lot of numbers here. This number at the very bottom of the chemical, of the NMR spectrum represents the chemical shift. And these numbers right here that are specifically under each peak represent the integration values. They're usually rounded to the next integer, okay, for a variety of reasons. Aldehydes don't integrate quite as well, but it's pretty close, okay? It's never precise unless you do things to the spectrometer to slow down the accumulation time or something like that, but it's usually pretty reliable. Okay, so we have a 3-to-1 ratio of these 2 peaks. Okay, all right, so we're going to do a problem here. You should pause the video and do this problem. And here's the problem, here's the task. Take the spectral data in the left column and match it to specific compounds in the right column, okay? And do it yourself and then restart the video when I go through the answers, okay? That's the best way to approach the learning process. All right, so there's no specific correlation across the page. That would make it too easy, so we don't really make them that easy. Okay. If we look at the types of protons that we have here, this CH3 and this CH3, these are equal, right? And this CH2 here is different from the CH3s. All right, so we're going to expect to see a 6-to-2 ratio in our integration values here. And when you look at an NMR spectrum, you can't tell 6-to-2 from 3-to-1. All you get is the ratio. So it's best to reduce your fractions. All right. In this one, every proton is equal to every other proton. Okay, so this we're just expecting one signal. Here, it's a bond line diagram, so we're not seeing the hydrogens, but this is a CH3. This is a CH3. So we're expecting this to also be in a 6-to-2 or 3-to-1 ratio. And this last one, yeah, so remember these two here are equal by symmetry. In this last one, we're expecting a 3-to-2 ratio. Okay, so we have 2 of them in a 3-to-1 ratio, and the other 2 have different ratios. So these are our signals that are coming in the 3-to-1 ratio. Okay, a peak at 4:1 and 3.8 and a 1 to 1.5 ratio. That's this one. Okay, and peak at 4.1 is there, and the peak at 3.8 is for the CH3 right here. Okay, this one has only one peak, therefore it has to be that one. Oops, sorry. Oops, I wish I had a go back feature. Has to be that one, right? Okay. Yeah, okay, all right, sorry about that. Okay, so that's that one. Now we have these other two molecules. All right, so these two hydrogens are on the same carbon as a chlorine. This is going to be, expect this one to be at about 3 to 4 parts per million. This methyl group, these C8 carbon, these hydrogens are on the same carbon as another carbon, this carbon right here. The chlorine is one atom further removed. So we're going to expect something much less for this one. We'll say certainly less than 3 ppm. Or probably more like 2, something like that. Okay. This one we also have a 3 to 1 ratio, but this is these hydrogens here are on the same carbon as an oxygen. We're going to expect this one to be about 3 to 4. These two hydrogens on the same carbon are on the same carbon as 2 oxygens, so we're going to expect a chemical shift substantially higher than 4. There. All right. So this peak here, this is in a 3. One peak's at 3.7, one's at 1.7. This is much better for this match than for the other. And here we have a peak that's a lot higher than 4, and one at 3.3, and that's this one. All right, I'm going to advance the slide, which is basically just going to have the answers, but in a much neater fashion without all these markups. So there we go. There are the answers in a much neater fashion. There they are as we got them. All right, so there's the answers. Okay, so one of the things about these compounds here, they were carefully designed so that they would have very simple signals. Okay, when we have adjacent protons, the signal becomes more complex. Okay, so let's look at the spectrum for this compound right here. What we see here is HA isn't, the signal for HA is actually 2 lines. The signal for HB is also 2 lines. And this has to do with the interaction of the external magnet with the hydrogens of HA, and how HA's 2 spin orientations can affect HB. All right, so let's observe HA here. So notice that HA, we're looking at the spin-aligned configuration. Okay. And now, how does this configuration interact with HB? Well, they can both, if we have one of the HBs aligned, okay, this is a lower energy situation, and if the adjacent HB has an orientation that's opposed to HA, this is the opposite higher energy configuration. So we have 2 different spin states. When we observe HB, we see the same thing going on due to the magnetic fields of HA. So each of these lines are split into 2 distinct spin states, okay? And we call the pattern that we're looking at here a doublet. Okay? All right. And this one is also a doublet, often abbreviated D. Okay, HA is going to be split into one slightly lower and one slightly higher energy state due to the interaction with HB's magnetic field. There's also going to be two patterns called a doublet. Okay, and HB will also be split in a doublet due to its interaction with HA. All right, let's look at a more complex situation. This is 1,2,2-trichloroethane. All right, HA, there's only one proton contributing to the HA signal, so it's a little bit smaller. And there's two protons contributing to the HB signal. All right, so if we look at HA, it's actually split into three lines called a triplet. Okay, and these lines are in a 1:2 ratio. Now, why is that? Okay, so let's do the same analysis here. We've got to consider now that there are two HBs. All of them can be aligned. This is the lowest energy situation. We can have either one of them opposed and aligned. Okay, and there are two ways to do that. I can't draw these on the same line because I don't really have enough room, but we call this the half-aligned configuration. These are the same energy, really, or degenerate. And the highest energy situation is where both of HB have the opposite spin configuration of HA. Okay, so we have four different spin states, but these middle two are equal to each other. So there's twice as many of them, and this is how we get the triplet in the 1:2 ratio. The 2 is due to the fact that there are two different orientations that can give rise to this middle energy spin state. Okay? And therefore HA is going to be split into three lines based on the interaction with the magnetic fields from HB, both of the HBs. The middle line is twice as big since it arises from two different but energetically equal spin states. Triplet often has the abbreviation T. Okay, HB, it's twice as big as HA because there are two hydrogens contributing to HB. This only split into a doublet. This is because if we look at the hydrogens on the adjacent carbon, there's only one of them. And this becomes like the situation before where there's only one hydrogen on the adjacent carbon. You got a doublet. Okay, so we can look at the pattern we have and tell how many hydrogens are on the adjacent carbon. Okay, and this simple pattern is called the N+1 rule. Okay, if we don't have any hydrogens on the adjacent carbon, there's no splitting. We're going to see a pattern that's called a singlet. One adjacent hydrogen, it's called a doublet. Two adjacent hydrogens, this one in blue here is going to be split by both of these. It's a triplet. And there's three coupled hydrogens in this molecule here, and it's actually split into a quartet, which has the abbreviation Q. Okay, that's not a good Q. All right, what you're seeing starting to emerge here at the top here is one, two doublets in a 1:1 ratio, three in a 1:2 ratio, and four peaks in a 1:3 ratio. This is Pascal's triangle. And as you get more and more hydrogens on the adjacent carbons, you can start to see how the peaks correspond to the Pascal's triangle. Okay? All right. So we have a signal that's split by a lot. It's important to recognize that it's going to be a little hard to see the outer lines. Okay? The line in the middle of this last one here, we can go higher. This is a quintet. A sextet and a septet. When we get to 7 lines, the line in the middle is 20 times as big as the line on the end. Therefore, it's when we have a signal that's split by a lot, it's hard to see the outer lines, okay? And a lot of students are really looking for all 7 lines of a septet, but sometimes, unless it's blown up to a really large value, you often can't see it. All right, so at the bottom of this slide, we have the rules for coupling. The number of lines, called the multiplicity, is equal to the total number of hydrogens on adjacent carbons plus 1. The lines are in a ratio predicted by Pascal's triangle. Only hydrogens separated by 3 or fewer bonds couple significantly. If you take the more advanced class, you'll see some exceptions to that, but in this class, we're going to sort of stick to 3 bond being the maximum coupling that we see. Okay, you can usually see longer coupling if you blow your spectra up, but I'm not going to blow them up for you. We're just going to look at the large couplings that you get by having hydrogens separated by 3 or fewer bonds. And this last point is that hydrogens that are equal by symmetry do not couple. This is a little bit of a simplification. This is the apparent result. There's actually coupling. It's just that it's not visible. Okay. All right. Okay. So when you look at the spectrum, these are the rules, are the predictive rules that you should be looking for. All right, so notice the number of bonds that are separating these from the coupling partners is always 3. There's 1, 2, 3 bonds that separate this hydrogen from that hydrogen. So these are the typical 3-bond coupling. 3-bond coupling is often referred to as vicinal coupling. Okay. All right, so let's do an exercise here again. You should do this yourself. Pause the video, do it, and then come back and see the answers. We're going to predict the coupling patterns for each distinct proton in this in each of these 4 molecules. Okay, so in this first one, what we're going to see here is that these 3 hydrogens, these 2 methyl groups, are equal to each other. Their signal is going to be add together to make it as intense enough for representing 6 hydrogens, but there's only, if you look at this carbon and what we would call the adjacent carbon, that's the adjacent carbon, there's only 1 hydrogen total. Therefore, these methyl groups are going to appear as doublets, 6 hydrogens. Okay? This hydrogen here is split quite heavily. Okay? The ones I'm writing in check marks are actually adjacent hydrogens. Okay? This hydrogen is 3 bonds away from 3, 6, 8 different hydrogens. Therefore, the pattern we're going to see is a 9-line pattern. I think it's called a no-net, but there's no official name for that. And finally, we're going to look at this last signal here. And if you look here, these hydrogens are separated from only this hydrogen by 3 or fewer bonds, and thus this is going to be a doublet. Okay, what do we have for the next one? Okay, for the next one, the methyls look kind of the same. They're both doublets, 6 hydrogens. This hydrogen here is going to be a 9-line pattern or a no-net. This pattern here for this carbon, for these hydrogens, well, this is an adjacent hydrogen, and these are hydrogens on adjacent carbons, and this is a hydrogen on adjacent carbon. There's 1, 2, 3 hydrogens total on the adjacent carbon relative to these 2 hydrogens. Thus, this signal here is going to appear as a quartet. This signal here, we have these 3 hydrogens and these 2 hydrogens. There's 5 hydrogens total. Add 1, and we get a sextet. and this last one, this methyl at the end of the chain, is going to appear as a triplet, okay? Because the only hydrogens on adjacent carbons are these two on this adjacent CH2 group. All right, and this one down here, it's important to recognize that we have a plane of symmetry that makes half of this molecule look like the other half, okay? So the proton here is going to be singlet. The nearest additional proton is this hydrogen. However, if we look at the number of bonds, there's 1, 2, 3, 4. This hydrogen is too far away to couple significantly with these hydrogens. So this is going to be a singlet. Okay? This hydrogen here, how far away is it from the nearest hydrogen? Well, we've already looked at how it's 4 bonds away from this methyl group. And if we look here, there's 1 separating it from carbon, 2, 3, 4. So there's no coupling across the oxygen because these two hydrogens here are too far apart. So this one is also going to be a singlet. This one's going to be a triplet. And this one is going to be a triplet as well. Ideally, you might think, shouldn't it couple to this? Well, these two are equal by symmetry, so there's no apparent coupling in the NMR spectrum. Okay, and finally, let's look at this aromatic system here. We'd expect this hydrogen here to be a singlet. These two would be a doublet because the only adjacent hydrogen is the one that I've shown here in green. These are equal to each other, so the peaks for this hydrogen would be twice as large as for either of these. This hydrogen here would be a triplet because there's 2 hydrogens on the adjacent carbon. There's a plane of symmetry in this molecule as well. All right. Okay, again, the rules of coupling are a little bit more complex. I'm just simplifying it. There's a complication that chiral molecules arise from chirality, but I'm not going to cover that here, and that's something that's for a more advanced class. Okay? All right. All right, so let's look at an actual NMR spectrum. This is the NMR spectrum of 2-hexanone. Okay, and we can see in the spectrum for 2-hexanone, 1 singlet for this hydrogen right here, and here's our singlet at 2.1. Remember, this is the chemical shift, this is the integration. Approximately 3 hydrogens are giving rise to this signal. Okay, 2 hydrogens give rise to this triplet here, and that's these hydrogens here. Okay, actually I don't need to do that because I have the chemical shift underneath. Sorry about that. All right, these 2 hydrogens here are appearing as a 5-line pattern, and that's this pattern here, or a quintet or a pentet. Okay, these are appearing. These 2 hydrogens are split by 5 hydrogens. Therefore, n+1 would give us 6 lines. So here we're seeing the 6-line pattern, or the sextet. And finally, we have another triplet. That's this one. Notice that we have 2 triplets. We can tell them apart because one integrates for 2 and the other integrates for 3. Right? It's 2, almost 3, almost 2. Okay. All right. And this spectrum here is exactly what we expect. Okay, so here's an exercise here. We're going to match spectra with compounds. I'm going to do all my work on this page, and then we'll advance it to a page where there's nothing but the answers. But you should pause the video and try to do it yourself. Okay, so let's match spectra with compounds. All right. So there's only 3 spectra and 4 compounds, right? 4 compounds. These are the N, iso, sec, and tert butyl chloride. Okay. All right, so let's look at what we expect here. All right, so in this one, we expect a triplet, quintet, sextet, and triplet. And this one here is going to have a high chemical shift greater than 3. So let's look at what we have there. This spectrum here, the long one here, actually fits perfectly, right? And this is, in fact, N-butyl chloride. We have the triplet, we have another triplet way down here, and then a quintet and a sextet. This one, this hydrogen with a high chemical shift is supposed to be a sextet. And if you look at above 3 ppm, none of them have that. So this is the one that not present. Okay, in a chiral molecule, sometimes these are going to appear as different signals. This has to do with the fact that they're technically not equivalent protons because of the adjacent chiral center. However, that's a complication that in the examples that I look at, I'm going to try to eliminate systems that have that because, again, we sort of have to respect that this is one chapter in a course or 2 courses that cover like 26 chapters. So we can't go into every nuance of NMR spectroscopy in one course. All right, in this one, isobutyl chloride, we're expecting our high chemical shift protons to be a doublet, no net, and these methyl groups all together to be a doublet. And this one you'll find actually corresponds very nicely to this spectrum right here. All right, so again, I've talked about this, but this is a heavily split pattern and no net. Some of you may say, this can't be the answer because if I count the lines 1, 2, 3, 4, 5, 6, 7, I only see 7 lines. How come I'm not seeing 9? This is because this is just so puny. Remember, even when you're split into 7 lines, the outside line is 1/20th the size of the inside line. So that's not a reliable method, counting the lines when you have a lot of lines. So there's far better methods or far more reliable methods than just counting the number of lines in heavily split peaks like this. But we do see that we do have 2 hydrogens, a doublet, and 6 hydrogens, a doublet. That's perfectly consistent with that. Okay, this last one, this is the spectrum right here. It's a single peak, and what you see here is that every hydrogen is equal in this one. We also see that since every hydrogen is equal, of course, there's not going to be any coupling, and that's T-butyl chloride. Okay, so that's our matching problem. Okay, here is just the answers that we looked at before. Now let's move on. Okay, here's another matching problem. Let's match the compounds with the spectra here. Okay, in this one, I've also got the spectra listed here. Okay, as well as pictured. Some of these spectra have peaks that we call multiplets. And this is when we have overlapping signals, and we can't tell what the signal is because of the overlap. The overlap makes it messy. Okay, it's important here to distinguish the difference between aromatic signals and hydrogens at sp3 carbon. Notice that each of these spectra have a little break here. This is because there's a large section of the spectrum that doesn't have any peaks, and we want to blow it up so that you can see what is what. All right, so what we see total, there's 4 hydrogens in the aromatic region. Let's just look at ratio of hydrogens at sp2 carbon to hydrogens at sp3 carbon. Here it's 5 to 2, 4, 7. Here it's also 5 hydrogens at aromatic carbons, 7 hydrogens at sp3 carbons. Here it's 4, and then there's 2, 5 and 8, 4 to 8. And here it's also 4 to 8. So here we have 2 4s and 2 5s for the aromatic region. So we can sort of separate it that way. All right, so let's look at this first spectrum. We have 4 aromatic signals. Okay, and if we look at our signals in the hydrogens at sp3 carbon, we have a quartet, 2 hydrogens, singlet, 3 hydrogens, and another and a triplet, 3 hydrogens. Okay, all right, so both C and D kind of look alike as far as this goes. We expect the CH3 to be singlet, quartet, triplet, singlet, quartet, triplet, so we can't really tell here. But what we can see is, let's look at the aromatic region. Here, there's quite a few different types of aromatic signals here, whereas here, there are many, there's really all the aromatic signals are equal here. And we kind of see that here, that there's a little bit more symmetry to the situation. Technically, these aren't equal to each other, but a methyl and an ethyl have such a similar effect on chemical shift that we could imagine that they would all come at the same place. Okay, so in the first one, we're going to assign it to the meta-isomer because there's less symmetry of the aromatic system. This one we're going to assign to the para-isomer, which has greater symmetry in the aromatic system. Notice that the hydrogens to the sp3 carbons look exactly alike in both cases. All right. In the other two, we have a N-propyl group here and an isopropyl group here. The thing to note here is that these hydrogens are equal, and we expect in V that our hydrogens at sp3 carbon, these 7 hydrogens, are going to be in a 6-to-1 ratio. And here we don't have this symmetry. We're expecting CH2 different from this CH2, different from this CH3. And we're expecting the hydrogens there to be in a 2-to-2-to-3 ratio. Well, notice here the hydrogens are in a 2-to-2-to-3 ratio. Therefore, that one is the N-propyl one, A. And this last one, the hydrogens are in a 1-to-6 ratio, and this is our isopropyl benzene here. Okay? All right. And the benzene rings, we can't really tell them apart. Both of them are expecting kind of similar patterns. Okay, we're going to look at some of the complications of overlapping signals in the next few slides. Okay. The n+1 rule is based on an approximation that the degree of coupling is equal amongst all the hydrogens that are in the coupling pattern. Sometimes we can get failure of the n+1 rule. And again, this is a concept that I'm going to say, if you want to see failures of the n+1 rule, that's going to be talked about more extensively in a graduate level spectroscopy class. In this class, I'm going to try to pick examples that actually follow the n+1 rule. All right, so this one, we'll just look at it. If we look at HC, or HB here, this is the interesting one. It's the degree of coupling to HA is much higher than the degree of coupling to HC. And if we look at the pattern for HB, it doesn't follow the n+1 rule. It's called a doublet of triplets. HA is the doublet you expect it to be, and HC is also the doublet that you expect from coupling to HB. But HB itself looks a little bit different, and this is due to the fact that the trans coupling on an alkene is one of the strongest types of coupling you can have. Okay, so if you analyze the signal here, you'd have to do something called what we call a tree diagram. Okay, HB is split by a very wide margin by HA into these two magenta lines here. And each of the magenta lines is split to a smaller degree by each of the HCs. The first one splits it into a doublet, and then the second one splits it into a triplet. Okay, and this is where we get the doublet of triplets. Notice these middle lines in bold are twice as big. This is because each of the HBs is coupling identically, we'll call this number J, okay? Each of the J values is totally identical. So when they're identical, this is the origin of the n+1 rule. These middle lines come exactly on top of each other, and that's where we get another way of looking at the triplet, okay? And because the value for HA is much larger, the lines don't coincide, okay? So that's why we have this more complex pattern. Again, I'm going to try to, or if a molecule doesn't follow the n+1 rule, I'm not going to have it as some unknown yet that you have to assign the structure for it. All right, here's another complication, alcohols. Because of hydrogen bonding, all right, HA and HC here are going to actually be exchanging rapidly, and no relationship is ever established, okay? Thus the OH proton, even though it's only 1, 2, 3 bonds separated from HB there, or 1, 2, 3 bonds HA to HB, we're still going to see a singlet because there's no because of this rapid exchange. There's no coupling relationship established. Okay, the CH2, the OH is going to appear as a singlet, and the CH2 that's adjacent to oxygen is going to appear as a quartet. Its only coupling is to the CH3 group and not to HC. Okay? All right, so here's an example, N-butyl alcohol. And what we can see here is that we have, that is a triplet. This hydrogen here is a singlet. These two come on top of each other, and there's this peak right here, and the CH3 is a triplet, and it comes right there. All right, and I'm going to say that, notice here that we have a very wide chemical shift range, 1 to 5 parts per million. This is because this is concentration dependent. A hydrogen bonding system has a higher chemical shift than if it's not hydrogen bonded, and this leads to different chemical shifts at different concentrations. So the OH signal is very concentration dependent. All right, so let's assign a unique structure to an alcohol that has the formula C5H12O and displays the following spectrum. At 3.3, it's got a singlet, 2 hydrogens. At 2.1, it's got another singlet, 1 hydrogen. And at 0.9, it's got a singlet, 9 hydrogens. Okay, so when you have a system like this, you have a formula. You have, notice that it's an alcohol. So we can say that this is our structure, C5H11OH. We just have to figure out what C5H11 is, okay? So 3.3, we have a singlet, so that means that it can't be coupled to anything else. So this is our CH2OH group here. And thus we have to have C4H9 over here. And we have to choose a C4H9 so that there's no coupling. All right, we also have a 9 hydrogen singlet, and that's, we have to have, and the only way you can really get this is to have 3 methyl groups that are perfectly equivalent to each other. So that's our structure right there. Okay, this is the only structure that would fit this. This is called neopentyl alcohol. Okay, let's look at some other complications. One complication is accidental isochrony. We've already seen this in one of the spectra before. These are non-equivalent hydrogens that just coincidentally happen to have the same chemical shift. They act like protons that are equivalent by symmetry. So here is the spectrum for toluene taken on a 90 megahertz machine. Okay, and notice that we have what looks to be five hydrogens a singlet. Okay, now that's not predicted when you do a symmetry analysis of the situation, right? The orthohydrogens in red are not equal to the metahydrogens that are in blue, and not equal to the single para-hydrogen that's shown in orange. You're expecting 3 hydrogens in a 2 to 2 to 1 ratio. Well, it turns out that the methyl group just doesn't have a lot of effect on the chemical shift, and all of these have very similar chemical shifts. So because they have the same chemical shift, they kind of act like they're equivalent by symmetry. You see no coupling. This would sometimes, people to distinguish that would call this an apparent singlet. Okay, if you go to a higher frequency, sometimes you will see coupling when you didn't see it at, or go to a more powerful spectrometer, you'll sometimes can see coupling, but on this machine, the 5 aromatic protons are acting as if they're equivalent. All right, here's nitrobenzene. Nitro is a strong electron withdrawing group and pulls and separates the chemical shifts quite dramatically. Here you do see 3 sets of protons in a 2 to 2 to 1 ratio. The one that's really close to the electron withdrawing nitro group has the highest chemical shift. It's a doublet here. The metahydrogens are a triplet, and the parahydrogens are a triplet. We can tell the metas from the paras by the integration. This triplet is bigger than this triplet. They're in a 2 to 1 ratio, so these are the meta para, and that's ortho. Okay? All right. So you might get an accidentally isochronous situation. You might have them different. And sometimes if they're different and they overlap on top of each other, but they're not accidentally isochronous, you get a messy pattern that you can't interpret, and that's called a multiplet. All right, let's look at a multiplet here. This is vitamin D3. It has an interesting complex NMR. You probably say to yourself, this is going to have a lot of hydrogens, right? And a lot of non-equivalent hydrogens. All right, you sort of get the idea here that there's tons of hydrogens, okay? A person that's trying to interpret this would probably give up out of frustration. This is called a multiplet. We can't tell the patterns because of signal overlap. Okay, so there's lots of hydrogens, but we can tell certain specific hydrogens here, okay? These two hydrogens are alkene carbons, and they're doublets. They're not equal to each other, therefore we're looking at these two hydrogens here. These two hydrogens are on the same carbon. This is actually only a 2-bond coupling because one of them's E, one of them's Z. They're not equal to each other, and therefore these hydrogens are here. It's not a doublet, it's two singlets. Okay? This hydrogen right here is expected to be much higher than any of the others, and we can see this one here. The signal's not blown up enough, but it should have at least 5 lines, should be a quintet. Let's see, what are these two? I'm not sure here, but I'm guessing that they're probably these. Okay, this methyl group here is going to be a singlet. And we can see that one of the methyl groups is definitely a singlet, whereas each of these is a doublet, doublet, and a doublet. And we have kind of 3 peaks that are overlapping here. These are 3 doublets. So we can't completely assign the spectrum here because of signal overlap. We can only look for specific signals. We try to get as much information as we can from a spectrum like this, but again, there's a lot of signal overlap, and we won't necessarily be able to assign every signal to a specific proton in the molecule. Okay, so this is where this one is going to end. And the next topic we're going to look at is the carbon-13 NMR spectroscopy.